Hi everyone, welcome to my YouTube channel. In today's video, I'm going to be going over a LeetCode problem 127, which is tagged as hard on LeetCode. Well, I'm currently preparing for a technical screen interview, and I just want to solve some problems to be able to work on my communication better. All right, so let's look at the problem and then I'll discuss how I think we can go about the solution to this problem. Yeah, so here we have a transformation sequence from the word beginWord to word endWord using the dictionary word list in a sequence of words. So here we have a begin words up to, then we have sequence of words S1, S2 up to SK, such that we have these following conditions. The first one is that every adjacent pairs of words differ by a single character. That's the first condition. And then we also have a condition that every SI for all I in between 1 and K is in the word list. So all the sequence we generated that is being generated has to be from the word list. And then the begin word does not need to be in the word list. Okay. So that's very important. And then also the last sequence of word being generated must be the end word. Okay, so and then we are going to be given two words, which is the begin word and the end word. And then we also be going to be given a dictionary of word lists. So our goal is to return the number of words in the shortest transformation of sequence. And yeah, so this sounds to be like a graph problem because we want to start from a begin word, then we want to go to a particular end word. We want to sort of traverse a particular path. And since we want to find the number of words in the shortest transformation of sequence, the traversal we are going to be using here would have to be the breadth first search. Okay, so breadth first search is very good with finding shortest distance or shortest path in a graph. Okay, and then if we could not find that word, or if the beginning word is not part of the word list, or if the end word is not part of the word list, then we return 0. Okay, so if we look at this example here, for example, we are given the input, which is going to be the begin word. Here, for example, is it, HIT, and then the head word here is cog. So we want to be able to traverse a particular path such that if we look at all the sequence of words, for example, HIT, we look at that to be this has to be changing at the second character, we have HOT, and then changing at the first character here, we have DOT, and then changing at the last character here, we have DOG, and then changing at the first character again, we have COG. Again, don't forget that the adjacent words, the adjacent pairs here must differ by just a single character. Okay, so if you look at all these things, they all differ by just a single character. Okay, and also this, they all differ by single character. And then in the second example, if we have a situation whereby the word list is not part of the end word is not part of the word list, then we just return 0. Okay, so let's look at how we can solve this problem. I'll switch my screen now, and then let's discuss how we can solve the problem. Now, from the question given, we have the begin word to be, for example, in this case is heat. And then we also have the end word. End word here is, in this case, is cog. And then we are given a list of given word lists, which we have in this case, we have this to be hot, dot, cog, dog, lots, cog, log, and cog. Okay. So our goal is that we want to start from heat and then change this by one character all the way to cog. We want to find out all our way to cog. Now, in this case, we can see that since cog is part of the word list, that means we want to find that path, and then we want to find the shortest path to cog. Okay, so to even think about this problem in the first place, right? Thinking about it in terms of graphs, let's say we have starting from our starting node, which is heat, and then we want to look at what would be the neighbors of heat in this case. Okay, now to think about the neighbors of heat, again, we can think about it by mere looking at, okay, to change heat at one by one character means that it's either we have change it at the first character. So here it's HIT, or we change it at the second character, which is H star T, or we change it at the last character, which is HI star. And then what will be the corresponding element? What will be the corresponding word in part of the word list? Well, the only word that corresponds to all these three conditions would have to be hot, HOT. That satisfy this any of these conditions, it has to be hot. Any other one doesn't satisfy this condition. Okay. Now let's look at this word hot itself. Let's consider the neighbors of hot. Well, again, if you look at the three possibilities of hot being changed at one character, it's either we change it at the first character, which is H star OT, or we change it at the second character, which is H star T, or we change it at the third character, which is H O star. And then if we look at this word list here, well, what would be the corresponding neighbors or the appropriate neighbors in this case of HOT? Well, it's either it is changing at the first character, that either we have D or T, which is dots, or we have lots changing at the first character, LOT, and all other ones, or the other one would be have to be then looking at this, well, this has to be HIT. Okay. Now we can see that again, if we look at the neighbors of heat, we can consider the neighbors of heat to be hot from just this first example here. And then we can also see that when we look at the neighbors of hot, we can see heat there. That means this is like an undirected graph. So if heat is connected to hot, definitely we should also see that neighbors of hot should be part of the heat. Okay. And also, let's look at one more example. For example, let's look at dots. Okay. And then if we look at what are the three possibilities of dots, well, the three possibilities of dots has to be, it's either we have dots changed at the first character, which is OT, and then we have changed at the second character, or we have dot changed at the third character here, which is going to be D O star. And then if we look at what is the corresponding element, or what is the corresponding word in this list, well, again, the words here should be lots. It's either we have lots, or we have hot, or we have dog. Just me looking at last character, dog. Okay. And then we can again looking at this, since hot is partnered with dots, that means dots must also be partnered with lots. So that means that this is an undirected graph. So we should have that situation. So we have this is to be dots. And again, we have dots is connected to dog. And again, don't forget that hot is connected to lot. So that means we can sort of draw lot somewhere down here. Okay. And then we can also have dots is connected to lots. Okay. So we can have this set of relationship. Okay. So we are good so far. So the neighbors of dots would be lots, which is correct. This is lots. Hot, this is hot here, and dog, which is DOG here. So neighbors what do we mean by neighbors? That means neighbors means they changed by one character. If you look at the adjacency, like if you look at the adjacent nodes, you would see that they changed by just one character. So that's what we mean by neighbors of that. Okay. So now if we try for dog, for example, now dog changed by just looking at just one character. So dog changed here by D. First character here is going to be DOG. Changing at the second character is going to be D star G. And then changing at the third character here is going to be D O star. And then what will be the corresponding values here? Well, corresponding values here has to be COG, LOG, and also DOT. Okay, so DOT coming from here, LOG and COG coming from here. Okay, and this doesn't correspond to any other thing aside from dog. Okay, well, again, so what would be the neighbors? What are the neighbors of this in this case now? Well, the neighbors here would be um again here we're going to have the neighbors here to be for dog. It's going to be cog, so cog, and then also log, log, and also dots, so which is undirected here. Okay, and then if we try it for all other elements here, we will find out, for example, for cog, for log, and then we can sort of fill this up here. Okay, just we can confirm that if you change log at just one character, you would get to cog. If you change cog at just one character, again, you get to log. And then if you change cog at one character, well, you also get to dog. And if you change log at also one character, you can also get to dog. So we have this relationship here. So we have this graph here. So again, so since we have this graph here, we can sort of traverse our graph using BFS. BFS considers it's a level order traverser. It looks at it, it prioritizes the level when it's being traversed. Okay, so if we start from heat, we can move to hot, we can move to dots, we can move to dog, and then we can move to cog. So this is like 5 nodes. So we can just count the number of nodes here, which is going to be 5. So this is what we want to do. So what we want to do here is that we want to start from a particular starting point here, which is going to be heat. Then we want to get to the end point here, which is cog. Okay. Now, how do we do that? Now, to traverse this, we want to build the adjacency list. But to build the adjacency list here is not quite obvious, and sometimes it could be inefficient. Okay. So the trick here is to build a pattern. So what do I mean by a pattern? So the pattern here is more or less like you having, like, for example, we have list of buckets. So we can think of a bucket this way. We can have list of buckets. And then we can label that bucket. For example, what do I mean by labeling the bucket? For example, we could label this to be H star T. We could label this H star T. We could label this star OT, for example, and then we could label this star OG, and so on and so forth like that. We could also label this HI star. Okay, and then we can look at what would be the appropriate elements in this bucket, or items in this bucket. Well, the proper elements in this bucket are values from this word list that changes that's you can sort of fill this particular element here. For example, if you look at H30, the appropriate element here would be either HIT or HOT. And then if you look at, for example, that star OT, well, the appropriate words here would be it's either you have HOT or you have DOT or you have LOT. Okay. And then you can also, this example, L star OG. So you could have DOG, LOG, and COG. Well, the advantage of this is that we could, from a particular word here in the bucket, we could get to all other neighbors in this particular bucket. And that's the importance of using this kind of structure or data structure for representing our adjacency list. And then what will be the keys for our pattern? So I call this the pattern. These are the patterns rather. And then these are the patterns, and it contains the list of words that have the pattern. Okay, so let's come back to our coding. So we can now start coding since we have an idea of how we want to solve the problem. So we can now start coding right now. Okay, all right, so let's come back to the Python solution here. So we would like to start writing our code right now. Okay, so to do that, the very first thing I would want to do here is to convert my word list to a set. So let's do that. So I'm going to say word list. It's going to be being converted to a set. So I can say word list in set of word list. Okay, so this line of code just converts my given word list to a set. So then I can look up. So what do I want to look up? I want to look up if my endWord. endWord. It's not in the word list. So I want to return 0. Okay, so what I'm doing here is that if my endWord from this particular example here is not part of the word list given, then just return 0. Okay, then once I'm done with that, then I can go ahead and add the beginning word, because don't forget that we want to traverse from the beginning word to a particular end word in the word list. Okay, all right, so let's do that. So we can say the wordList.add. So since this is a set, so we can use .add, not .append. If that's, we use append for list, but we use add for set. So we can add the beginning word. Now that we have the word, the beginning word, so we can then go ahead and start creating the buckets for patterns. So I'm going to call that patterns, and then this is going to have what is the structure of the pattern? Well, it's going to be a dictionary. So to use that, I'm going to call defaultdict. So I can say from collections, I can import defaultdict, and then how do I want my pattern to look like? My patterns look like, well, it should have defaultdict, then the default values should be a list. Okay, it should be a list. All right, so what this does is that it creates a dictionary, an empty dictionary, and then it's assigned values to any key there, any key you try to add. It's assign a default value to be a list. Okay, that's just the meaning of that. Okay, so let's go back to the diagram I drew. So these are the patterns. So I want to be able to add, create this pattern here for each word. We can have like 3 different patterns. Then I can sort of append all the patterns based on the word list. Okay. All right. So let's do that. So that means that here we can see that for word in this word list. Okay. And then also I can also say for I in, that's for each character in range of the length of the word. Okay. So basically I want to be able to, so here, this is what I want to do here. Now, imagine I have the word heat. Okay, I want to be able to generate this set of strings here. So these strings here would form my key, because these strings are hashable. So I can make it as a key. Okay, so to do that, here is a trick. So I call this a pattern. And how does it look like? Well, since we are for I in range, so for example, if we are looking at the word beginWord HIT, well, the length of that word is going to be 3. So, and then if you are looking for range in something, so that means it's going to go from 0 to 2. So that's going to like 0, 1, 2. Okay. Now I can say, okay, for example, I'm going to take that word and slice it from, for example, I slice it from I. So this is going to be all the elements before I minus 1. And then plus, I'm going to concatenate it with a star. That's what I want to like. That's my key. Then plus word. And then also I plus 1 up the way to the end. So let's sort of understand what is going on here. Well, let's say we have, for example, we have the word HIT. So this slices it from the beginning. So this is all the way from the beginning. So we have here, this is going to be nothing. So here this is going to be nothing. And then append nothing to star. Then start with the star, then it slices it from 1 to the end. So if you look at HIT, for example, let's look at HIT. So here we have 1 till, so here because I is 0, so that means we have from 1 to the end. So here is 0, this is 1 to the end. So we have IT. That's the first loop. Then the second loop is going to be that's when I is 1. So when I is 1, so it goes from 0 to 0. It's going to be H. Okay, so because this is this is just going to take the first letter here. Then after that, it appends a star here. And then this is going to be from I plus 1, which is going to be 1 plus 1, which is 2 to the end. This is going to be 0, 1. So since we have then since I is 1, so that's going to be 2 to the end. So that's going to be T, starting from T. And then when I is basically 2. So again, we have 0 to 1. So that means this is going to be HI. Then add a star. Then eventually when I is 2, this is going to be 3 to the end. So since we are above that, so nothing gets added to it. So this is for the first word here. We are going to generate these 3 patterns. Okay. And then generating these 3 patterns. So what do we do with them? Well, we are going to put them in this word list here. So how do we do that? So well, we just say patterns of pattern. So pattern here is just going to be like one pattern here is going to be this. Then another pattern is going to be this, and then another pattern is going to be this. So basically for each of those patterns, I want to be now, what is the importance of this? Well, the idea here is that since we already have a default dict, so calling a pattern, like wanting to add a pattern, I'm just going to append. Since this is going to be a list, okay, because this is a dictionary, and then the default value here is a list. So if I call a particular key from that dictionary, well, it's just going to return back an empty list. Then I can append the word, so which is going to be a word here. Okay, so now what does pattern looks like? Well, I'm just going to copy a value of what I printed as the patterns. So this is what pattern is going to look like. So here is it. So we have, for example, H star T. So H star IT, like I said, star IT, it comes from heat. H star T comes from heat, okay, because it's appending those words, and HI star also comes from heat. Then if you go to the next word, which is hot, so this is star OT, which is hot here. And then again, if you change H star T is already is already here. Okay, so because it's a dictionary, so once once the key is present in that dictionary, it will just append that particular word we are looking at that point in time, which is HOT, which is this. And then since star OT is not part of the dictionary, to just create it HOT. Then it continues like that for all the words in that dictionary. Then we have this list. So this is what the pattern looks like. So it contains the bucket. So these are the buckets. I can think of this as the bucket. This is label for the bucket. Then what's inside this bucket? These are the words inside that bucket. Okay, and what is the importance of this? The importance of this is this. For example, if I'm looking at a word which is contained in a bucket, which is HIT, right? That means I can also see other words in that. I can also see other words or other neighbors in that same bucket. Okay, so for example, if I'm starting from heat, I already know that neighbors of heat would be hot. Okay, then I go to hot. What are the neighbors of hot? The neighbors of hot would be dot and lot. Okay, then from neighbors of dot, which is starting from dot here, I know that neighbors of dot here is going to be dog, and then neighbors of lots is going to be log. Now coming back to dog, neighbors of dog is log and cog. Okay, so since the neighbors of log is cog, that means I just move from heat to hot, from hot to dot, from dot to dog, then from dog to log. I mean, that's how my BFS is going to look like. So the next thing now is for us to write the BFS of this, just me looking at this. Okay, well, okay, so what I'm going to do is I'm going to leave this pattern here so that we can see how we can write the BFS of this particular problem. All right, so let's come down here. So I'm going to define my BFS, DEF, BFS. Then my BFS is going to take 2 words. First one is going to be my starting node, and then also the end word. So basically, because I want to check where uh, I want to trace from the starting node to the end word. Okay. All right. So again, since I'm using a BFS, so I would like to import a deque. So I can say from collections, I can import a deque or deque, anyone. So here we can sort of now import that deque here. So we can call our deque here. So the importance of this deque here, I mean, it behaves like a list, but then it has some special property with the fact that you can pop from the left. For a list, we can only pop from the right or from the end. So, but here you can pop from the left. So, giving that vibe of first in, first out property. All right. So since we're able to do this, well, next thing is that we want to add our node. So what nodes do we add? Well, I'm going to append q.append a tuple. So what's going to be what that first element is going to be my stats, and then the next element is going to be my node one. So basically, if our start is meant to be hit here, that means it goes in here, and then that means that's my first node being visited. Then I can also now another thing I also want to say here is that let's go back to this diagram now. Now, if you think about this for BFS, if you start with it and then you consider the neighbors of heat, which is hot, okay, then you move to hot. Okay, let's say we are now in hot. Now we want to consider the neighbors of hot. Well, the neighbors of hot is going to be heat, dots, and also lots. These are the neighbors of hot. Well, if we are to go back to like traverse that hot, well, we need to go back to heat again. Okay, so that's one factor about undirected graph. It sort of gives this traversing undirected graph, as you have to traverse it carefully. Well, one solution to this is to sort of create a set for visited nodes. Okay, so since I already visited this and I already processed this, then if I'm coming here, I don't have to go back here again. I sort of just move to the next node that is not being visited. Okay, so that's the idea here. All right, so to do that, I'm going to create what we call scene set. So I call it an empty set. And I can add nodes being visited. So in this case, I already visited the first node. So I can add scene.add. So I already visited the first node. So I can call it scene.add, and I add my first node, which is start. All right, so we are good so far. Now, for BFS, we want to start processing things now. So let's start processing our nodes now. Since we already added the first node there, which is the starting node. So while we have a queue, well, we want to process the first node, which is going to pop left. So that means we have current node, and then we also want to check the level. Now, for example, if we are popping the first element here, the current node is going to be the start node, and then the level is going to be 1. So we want to say q.popleft, and then after that, then we check if the current node is the end word we are looking for. So if that is the case, we can just return the level. If that's not the case, then we can now, here is the thing. We want to start taking in the neighbors. So to take in the neighbors, well, first thing first is that we also want to look at, for example, if we are looking at the word heat, what should be the neighbors of heat? Well, the neighbors of heat should be hot. Now, how do we eventually add the neighbors of heat in this case? Well, we can play the same trick we played in this first part here by defining what we call the patterns. Okay, so let's say for high in or for the characters in the range of the length of the words I'm looking at. So yeah, in this case, it's going to be the current node. For high in range of length of the current words, so I'm going to then go ahead and generate a pattern. Okay, so the pattern is going to follow the same structure. So again, I'm just going to copy this and then paste this here. And then change the word because the word we are looking at is the current node. Now, what is the importance of this? Again, still using the same style because we want to add the neighbors. Again, we are doing BFS. BFS means that you look at your current node, you process it. Now, processing it means that you want to add the neighbors to the queue. So how do you add the neighbors to the queue? Well, we look at all the possible values here, all the possible pattern here. What the possible pattern for the word hit is going to be star IT, H star, H star T, and HI star. So that's the current pattern. Now for this, we also want to do something. Now we want to add all the neighbors now. So we can say for neighbor node in. Now we can now go back now and say, fine, we already have list of patterns here. Now this is what our patterns looks like. So we can say patterns of, so for pattern, so for each of the pattern, for example, if I'm looking at star IT, then I want to be able to add, so I want to look at the pattern. So I want to look up the pattern here. So I already have the list of the patterns here. So I want to look at for each of the pattern. For example, this one now. That means it's going to grab this list. Okay, so we only have one pattern here, which is hit. Well, so again, we can now check that if the neighbor node is not in pattern. Again, don't forget that these are the nodes. Okay, but then we are using the pattern to arrange the nodes. Okay, the neighbors of the nodes rather. So for if the neighbor node is not in scene, so if the neighbor node is not in scene, well, you can go ahead and add it, neighbor node. So you can go ahead and add scene. So scene.add. So I can add the neighbor node, and then also I can then go ahead and add it to the queue. So queue.append. So neighbor node. Now to add to the queue, we have to follow the same structure as this. So here we have neighbor node, and then we also need to add the level, because this is the current level, which is 1, and we need to update the level by 1. Okay, so that's the idea. So what is this doing? Well, let's take for example that we are starting from this pattern here. Well, what this would process for neighbor node in this particular pattern. Okay, so this is going to be the only neighbor node for this, which is HIT, which is going to be added, which was already added to scene. So since this was already added to scene, then it's going to it's going to stop. This is not going to process. Nothing is going to happen here for the first iteration here. And then for the second, because we have for I in this first current word, which is still hit HIT, then it sort of moves to the second iteration here, which is H star T. Then then it comes back down here. That's the second pattern. Then it comes down here and it checks that for neighbor node in pattern. So these are the list this list here is going to come here. Then it goes for each of them. So it assigns neighbor node to HIT here. So if HIT is already in scene, then it keeps that. Then it moves to the next value here, which is HOT. HOT is not in scene. Well, it adds it to the scene list, and then it appends it to next value. So once that goes there, it goes to the next value. Okay. Then the last iteration for this, which is HI star. Again, it goes in. Since I already seen HIT, then that's the end for this particular operation of the current word. Then the current word now that needs to be processed would now be hot rather. It comes back here, which is hot. Then level here is 2. Okay, then it goes back to this iteration here. It comes back to this iteration here. Then it's processed just like the other way around. Goes all the way. So once I already see a particular value, then all other ones would skip. This would skip. since I already seen a hot, this will also skip. So there is a lot of like operation that is already being skipped here as a result of eliminating the duplicates from just as a result of creating that scene list. To eliminate a lot of duplicate operations. That's what I want to point out. So and then once we are done, if it goes all the way and it couldn't find it, then we can return 0. Okay, since we can't find it, so we can just return 0. And then once we are done with everything, we can now return the BFS of our starting word, which is going to be beginWord, and then endWord. So and then endWord. All right, so this is what we should have. So I'm just going to go ahead and comment this and see if this should work. Hopefully it should work. So yeah, so we have it to be accepted. So let me go ahead and submit this. Oh wow, so yeah, so this is a very good solution. I'm very happy about it. So let's discuss the time complexity of, let me see if I can analyze the time complexity of this. So the time complexity of this is m by n. Well, the real time complexity of this is actually, all right, so what is the time complexity of this? Well, to build for this word in word list, well, the length of word list is traverse through all the word list is at worst number of word lists, which is n. And for you to look through each of the words in the word list, so let's say the length of each of the word list is L. So this is going to be at worst L. So that means we have n multiplied by L. And then for us to do slicing here, so the operation for slicing is a list is going to be also at worst L. Okay, so this is going to be at worst L here. So that means for this particular case here, generating the pattern is going to be at worst n. So the time complexity at worst n multiplied by L square. And then for the BFS, okay, so for the BFS, we have a situation whereby we have to traverse through the list. So for each of the word, we generate. So for each of the words, we only generate L pattern. So that means the worst case scenario for this BFS is going to be n multiplied by L. N multiplied by L. Multiplied by L. So since these algorithms are quite different, okay, that means we can add them together. And then for worst case, we just pick the largest, which is this. Okay, yeah, so the time complexity here is going to be n multiplied by L square, which is very efficient. And also for the space complexity, right? So for the space complexity, so building of patterns here, building of these patterns here would take L n multiplied by L. So because we have because we would have n multiplied by L keys. And then for the scene list here, we would have the space complexity here to be the number of visited words, which is going to be at worst n. And then for the BFS queues, we're also going to have the worst case scenario to be time complexity of n. So n multiplied by L plus n plus on is still going, the worst case is going to still be on multiplied by O of n multiplied by L. So the space complexity is going to be n multiplied by L. All right. Thank you so much for watching my video. I hope you enjoyed this video. I hope you learn something from this video. And if you learn something and you really like what I'm doing, please support me by subscribing to my YouTube channel so that I can also upload more videos like this. And I'll see you in the next video. Thank you.